Welcome to podcast 14.1, Acids and Bases. As you can tell, I'm storing things in my cheeks. So if my voice isn't really right, that's why. Alright, on with the show.
All acids are sour, and if you think about the acids that you eat, like acetic acid in vinegar, or citric acid, or ascorbic acid, vitamin C that they put in some things, ends up being a little bit sour. And if you put a lot of it in, it ends up being really sour. As you know, acids react with metals. And the famous acids, you guys need to make sure you know these. But hydrochloric acid, you make in your stomach. That's what you help break down food with. People with pools use it to adjust the pH. And pickling steel is a fancy word for cleaning steel before you paint it or before you work with it to get rust and impurities off the surface. Sulfuric acid is the kind that you find in car batteries, and sulfuric acid has the added benefit of being able to eat through clothes, even when dry. I've lost quite a few pairs of pants and shirts over the years by leaning up against counters I thought there was no acid on in lab, and poof, there is some after all. But you never notice it till you get home and you put the clothes in the washer. So nitric acid, but it's used to make explosives, and then phosphoric acid is a weak acid, and it's used to get flavoring to different drinks like Mountain Dew. Bases are the opposite. They're bitter, they're slippery, and if you don't believe me, go home, grab some bleach. Your mom or dad probably has some bleach somewhere around. Just put a little bit on your fingers, rub it back and forth, and you'll notice it's really, really slippery. And that's because bleach is really a base. Famous members, sodium hydroxide, lye. They use it to unclog drains. So most clogged drains are clogged with grease and or hair. And what does sodium hydroxide eat through really well? Grease and or hair. So that's why it's useful for that. Potassium hydroxide is sometimes used in place of sodium hydroxide. Ammonia, you need to know ammonia is a base. That's NH3. And then baking soda is a good base that you can use around the house to maybe get rid of some acid, or if you have a little bit of acid indigestion, you can actually make up a solution of sodium bicarbonate, baking soda, and swallow it, and it'll help get rid of some of that acid stuff if you have too much acid in your stomach. We have 3 definitions for acids and bases. Arrhenius was the first one. Acids give off hydrogen ions or hydronium ions, H3O. I don't care which way you see it here. They mean the same thing for us. All acids give off H+, and we've learned that for a long time. HCl gives off H pluses and Cl minuses when it ionizes. Bases give off OHs, and you know that's true because I always told you that bases have OH. And when they mix together, the H and the OH get together and they neutralize each other and make water. And if you remember, back when we did rules of reactions, an acid and a base make salt and water. It's that water part that comes from the neutralization. That was the first definitions of acids and bases. It's the simplest, but it really doesn't encompass all of the possible acids and bases. So along comes this guy named Bronsted and another guy named Lowry. And Bronsted-Lowry came up with a different definition for acids and bases. They said acids are things that give off H pluses. Well, that's no different, right? But we're going to put H pluses in this case as a proton. And that's really what H plus is, because H typically has 1 proton and 1 electron. And if it becomes an ion, you lose that electron and you're left with a proton. Ta-da! Gives off H pluses. Those are protons. That's nothing new. The new one is down here. Let's think of bases as being proton acceptors. Here's what I told you a base is. Has hydroxide, right? Well, that hydroxide takes in H pluses. It accepts H pluses or protons and turns into water. I know what you're thinking. You're thinking, that's nothing new, Mr. Elegante. But what about this? Didn't I just tell you that ammonia, NH3, is a base? I think I did. So how is that a base? It doesn't have an OH attached. Well, if we look at the Lewis dot structure for ammonia, it has a hydrogen and a hydrogen and a hydrogen tied to it. And if you remember, it has a lone pair. That lone pair of electrons isn't doing anything. So along comes an H plus, and the H plus is down on its luck. It's very sad. It says, I don't have any electrons. I want yours. And ammonia, being a nice guy, goes, no, you can't have it. Well, because ammonia needs it. It says, however, you can come join my molecule, and by joining with my molecule, you can make the wonderful, delicious ammonium polyatomic ion. So ammonia is a base, not because it gives off OHs, but because it takes up hydrogen ions. It widens the circle of understanding of what acids and bases are a little bit, and that's helpful. The last one is Lewis. Lewis of Lewis electron dot structures was not worried so much about the protons, but about the electrons, because really, electrons are what drive chemical reactions. It's all about the electrons. So he said, let's not look at it in terms of who's donating protons, but instead let's look at who's accepting electrons, who's donating electrons. All acids are electron receivers. That makes sense because H plus has no electrons. So if you give it an electron, then that thing right there becomes a happy hydrogen. Yay! So acids do accept electrons. It's just a different way of looking at it. Bases are electron donors. Well, we just learned that. That's true. NH3 had a pair of electrons to give. It donated the electrons to a hydrogen. That works. That's a base. OH, hydroxide has a couple lone pairs of electrons that it can donate as well. Why am I saying all this? Because this is nothing new. These are all things that both Arrhenius and Bronsted-Lowry had already covered. Well, because let's think about this guy. BF3, boron trifluoride. Is that an acid or a base? Well, it doesn't have a proton to donate, doesn't have an H to get rid of, so it couldn't be an acid. It doesn't have an OH, so it couldn't be a base. And it doesn't really have a way to accept a hydrogen. But what it can do is, if you remember, boron trifluoride was weird in that boron trifluoride was happy with 6 electrons. So what if you walked over with something and tried to give it 2 more electrons? Would the boron accept 2 more electrons? The answer is yeah. If you try to give it 2 more electrons, then that becomes an electron acceptor. And if it receives the electrons, then it's acting as an acid. It just opens up our understanding of what can be an acid and a base. You run into lots of things in the world that aren't H plus acids or OH minus bases, but they still act like an acid or a base based on whether or not they give or receive electrons. So you guys just need to know this basic vocabulary. Monoprotic means 1 hydrogen. Yay, 1 hydrogen. Diprotic means 2 hydrogens. Polyprotic means more than 2 hydrogens. Now what does that mean? Well, HCl is monoprotic because it has 1 hydrogen. 2 hydrogens would be H2SO4 sulfuric acid, and polyprotic would be H3PO4 phosphoric acid. The words sound fancy, but really they're not. They just describe the number of hydrogens. A weak acid is one that ionizes weakly, or, that doesn't mean every week, ionizes a little, less than 5%. And strong acid is one that ionizes a lot, greater than 95%. And there really isn't a whole lot of middle ground in there, but those are good rough rules for you guys to remember. I have a way for you to remember your strong acid very quickly. Hickel, HCl, Hibber, HBr, high. The friendly acid, those are always strong. What else is strong? Well, if the oxygens outnumber the hydrogens by 2 or more, then it's strong. Let me give you an example. HNO3. Is HNO3 strong? Yes. The oxygens outnumber the hydrogens by 2, so that works. That's strong. What about H2SO3, sulfurous acid? Is that strong? No. The oxygens don't outnumber the hydrogens by 2 or more, so that one would be weak. What about H2SO4? H2SO4, that would be strong because it outnumbers. And what about H3PO4? That would be weak because it doesn't outnumber. That's how you know whether the oxy acids, you know, they have oxygen in them, are strong or weak. And then these are the 3 strong ones I need you to know. Anything else is weak. So if I said acetic acid, what is it? You would go, well, it ain't strong, therefore it's weak. A weak base is simply put a base that doesn't ionize very much. The easiest way to know this is ammonia. That's a weak base. That's the one I want you guys to know. The strong bases are going to be your group 1 hydroxides. My pen is not working very well. The group 1, that's supposed to be group, by the way. Group 1 hydroxide. So lithium, sodium, potassium, those are typically going to be your strong bases. The other ones, calcium, barium, magnesium, those are going to tend to be weak bases, but you get into a little bit of gray area there because you're not real sure exactly what to call them. But for now, just know that the weak one is ammonia, and then the strong bases are all the group 1 hydroxides.